Welcome to the Unit 1, Section 2 video on segment relationships. So in the last section we talked a little bit about our basic figures in geometry, points, lines, and planes. Well, we're going to go a little bit deeper into lines and talk about portions of lines, and that is a line segment. So let's start off by talking about what a segment is. It is a part of the line consisting of 2 points and all the points between them. Okay, so you see over here in the figure we have point C and point D, and we have a line in between them. This line does not go infinitely in both directions like a line does. This is a segment of a line, so it is finite. Okay, so we call this a segment. It is also called a line segment. Okay, so when we say the word segment, we're typically talking about a line, and if you want to put the word line in front of it just to kind of help you remember that we're talking about a line segment, then you can do that. Now, there are an infinite number of points on a line segment. Just like there are an infinite number of points on a line, there's an infinite number of points on a line segment, because no matter where you put another point on this line, you can always put another point in between those 2 points, and then another point between those 2 points, and that can go on forever. Now, the notation for this, you're going to use the 2 points on either end of the line segment, so C and D in capital letters, but instead of drawing arrows, we're just going to draw a line on the top. Okay, so a line without the arrows tells us it's a line segment. This can also be written the other way as DC. So that's segment DC or segment CD. Now, the endpoint is a point at one end of the segment. So now that we have a little bit of the knowledge of what a line segment is, much of the rest of the section is going to focus on how we work with line segments and how we use line segments to find things. So let's talk about measuring segments and congruency. In geometry, the distance between 2 points is used to define the measure of a segment. So take a look at this comic from Charles Schulz. This is Peanuts, and Sally is using a ruler for a school project. So she decides that she's going to measure Snoopy's mouth, which Snoopy seems fairly alarmed at. And after putting the ruler in Snoopy's mouth, well, she finds that it's hard to read a wet ruler. Snoopy's not too fond of the aftertaste either. We'll come back to this comic. That kind of sets us up to something that's going to be coming here in a moment. Now, betweenness. In the figure, point B is between points A and C. Okay? You'll find a lot of times in math, we are not very creative in how we name things. Okay? So betweenness is something that is between two other things. The distance between points A and B is written as the length of segment AB. And remember, when we're talking about a segment, we use a line on the top. Or we can shorthand it by just saying AB with no line drawn on top. If there's no line drawn on top, then it is understood that we're talking about the length or the distance of that line. So let's come back down here to the next day of the comic, where Sally is continuing to work on her school project. So she's going to try measuring Snoopy's mouth again. She puts it in Snoopy's mouth and reads that one lip is on the 6 and the other lip is on the 9. So lip to lip, that's 3 inches. Well, how did Sally come to that conclusion? Well, Sally placed a ruler so that one of Snoopy's lip was on the 6 and the other was on the 9. She could have placed the ruler so that one lip was on the 0 and the other was on the 3. In fact, 2 points on any line can always be paired with real numbers, so that one point is paired with 0 and the other is paired with a positive number. This correspondence allows you to measure the distance between any 2 points and thus the length of any segment. So this whole concept, the fact that she could have shifted the whole ruler over and started one lip on 0 to get that distance of 3, where the other lip would have been, the other side of his mouth would have been on 3. This idea is called the ruler postulate. And in the next page here, I give you the ruler postulate a little bit more mathematically. The ruler postulate states the points on any line can be paired with the real numbers so that given any two points P and Q on the line, P corresponds to 0 and Q corresponds to a positive number. The distance between points may be measured using a number line. And you see an example of that here below. On this number line, A is on 1 and B is on 5. Well, if we wanted to use the ruler postulate, we could shift A over to the left by 1 and B over to the left by 1, and that would give us our length of 4. Of course, here you can easily count it as well. To find the measure of segment AB, you first need to identify the coordinates of A and B. The coordinate of A is 1 and the coordinate of B is 5. Since the measure is always a positive number, you can subtract the lesser coordinate from the greater one, or you can find the absolute value of the difference. So it really doesn't matter which way you subtract, as long as you take the absolute value, you can still come to the same value. So let's try that. If we do the distance from A to B, we've got the absolute value of 5 minus 1, which is equal to the absolute value of 4, because 5 minus 1 is 4. Absolute value of 4 is 4. Remember, the absolute value always makes whatever is inside the absolute value positive. So if you have a positive number in the absolute value, you're going to get a positive number. If you have a negative number in the absolute value, it will become positive. Now the distance from B to A, if we do it backwards and we do the absolute value of 1 minus 5, we get the absolute value of negative 4, which again is 4. So we say that the measure of segment AB is 4, or you can notate it this way, AB equals 4. Now that we've done a little bit of content here, let's get into some examples. So example 1, we're going to determine the length of segment LM. Well, we can count that, okay? So we can count it from here, starting from L, 1, 2, 3, 4, 5, 6, 7. So we know the answer is 7. Let's do this mathematically. So we have LM equals the absolute value of, let's just take the top number, 3, and we'll subtract negative 4. Well, that gives us the absolute value of 3 plus 4, which is the absolute value of 7, which is just 7. So we counted it, and there it is mathematically. Now we could do it the other way. We could do negative 4 minus 3, which would have given us the absolute value of negative 7, which again would have been 7. Okay, let's talk about the segment addition postulate now. On the following number line, A, B, and C are collinear. Remember, collinear means they fall on the same line. So since A, B, and C are collinear, we can add segment AB and segment BC. So let's see what AB is. AB is 1.5. You can read that off the number line. You can also do it mathematically as it's presented here with the absolute value as we just demonstrated. Let's find the length of BC. Well, that's 1, 2.5. Again, mathematically presented here. Well, the length of AC is 1, 2, 3, 4, mathematically presented here. I can simply take the length of AB and the length of BC and add them together to get the length of AC, and that is the segment addition postulate. if Q is between P and R, then PQ plus QR equals PR. If PQ plus QR equals PR, then Q is between P and R. Okay, so basically it's the same statement both ways. It works in either direction. So back up here in this example, AB plus BC equals the whole thing, AC. So let's use the diagram here, P, Q, and R, to answer the following. Okay, we've got two different problems that we're going to do with this one. First, if PQ is 9 and QR is 28, then let's find PR. Well, let's start with the geometry step. I always want you to start with the geometry. We know since Q is between P and R, PQ, which is this segment, plus QR, which is this segment, equals PR, which is the length of the whole thing. Well, PQ is 9, QR is 28. So we know that 9 plus 28 is 37, and in this case, that is the length of the entire thing. That's the length of PR. For B, we again know that PQ plus QR equals PR. That's the segment addition postulate. But we need to find what PQ is this time. So PQ is what we're looking for. QR is 17. And PR is 21. Now if we want to solve for PQ, we simply subtract 17 from each side. So 21 minus 17, PQ equals 4. Okay, let's try example 3. So if EG equals 71, we're going to find the value of x. So we're throwing a little algebra back into the mix here. Well, we know the segment addition postulate tells us EF plus FG equals EG. Okay, that we know. This segment plus this segment gives us the length of the whole thing. So let's use that to find x. Well, we know that EF is 8x minus 17, so we're going to plug that in. 8x minus 17. We know FG is 5x minus 3, so we're going to plug that in. EG, we're told up here, is 71. And now all we have is an algebra problem. We're solving for x. So 8x plus 5x gives us 13x. Negative 17 plus negative 3, that's negative 20. We add 20 to each side. So 71 plus 20 gives us 91. And 91 divided by 13 gives us 7. So x equals 7. In example 4, we're asked to find TU. Again, we're going to start with the segment addition postulate. Okay? So we have TU plus UV equals TV. TU we know is 9x plus 2. UV is 5. And TV is 14x minus 8. We're going to start here because to find what TU is, we need to find x. And so we're going to use the segment addition postulate here to find x. So we add 2 and 5. That gives us 7. Then we're going to get our x's onto one side and the things that are not x on the other. So I'm going to subtract 9x from each side. So 14x minus 9x gives us 5x. And then we add 8 to each side. 7 plus 8 gives us 15. And then 15 divided by 5 gives us 3. Now, remember, read the directions. We're not finding x in this one. We're finding tu. We simply need x to find what tu is, because we know that tu is equal to 9x plus 2. So we're going to substitute in 3 for x, because we just found what x was. 9 times 3 is 27. 27 plus 2 gives us 29. So tu is equal to 29. All right, example 5. If JL equals 5x plus 2, we're going to find what JL is. JL is the length of the whole thing. Just like the last problem, we are going to use the segment addition postulate to find x, and then we'll plug x into JL to find the value for JL. Okay, so segment addition postulate, JK plus KL equals JL. So JK is 27. KL is 3x minus 1. And JL is 5x plus 2. All I'm doing is substituting things in. So 27 minus 1 gives us 26. We're going to subtract 3x from each side. That gives us 2x over here. Going to subtract 2 from each side. That gives us 24 here. And so x is 12. Now that we know what x is, we can find JL. JL is 5x plus 2. X is 12, so I'm going to substitute that in. 5 times 12 is 60. Add another 2, and you get JL equals 62. All right, example 6. If CE is 7x plus 4, we want to find x. So here we're back to just finding the value for x again. Well, segment addition postulate, we know that CD plus DE equals CE. So CD is x plus 3. DE is 8x minus 9. And CE is 7x plus 4. X plus 8x gives us 9x. 3 minus 9 gives us negative 6. Let's subtract 7x from each side. So that gives us 2x on this side. Let's add 6 to each side. So that gives us 10 over here. And divide each side by 2. X equals 5. For example 7, we're asked to find a few things. We're asked to find x and the length of SK, KY, and SY. So, as always, let's start with the segment addition postulate. SK plus KY equals SY. SK is 13x minus 5. KY is 2x plus 9. And SY is 36 minus x. Combine like terms on the left-hand side. 13x plus 2x is 15x. Negative 5 plus 9 gives us plus 4. And the other side, we still have 36 minus x. Okay, now let's get our x's on one side. So let's add x to each side. That gives us 16x here. Let's subtract 4 from each side. That gives us 32 here. So x equals 2. So that's the first piece of information we were asked to find, and there you have it. Now let's find each length. Let's start with SK. SK equals 13x minus 5. If we substitute in 2 for x, 13 times 2 gives us 26 minus 5 gives us 21. If you have to put that in your calculator, feel free to do that. ky is 2x plus 9. 2 times 2 is 4, plus 9 gives us 13. And then finally sy, we have 36 minus x. So 36 minus 2, which is 34. Don't really need a calculator for that one. So sk is 21, ky is 13, and sy is 34. And you can do yourself a quick check. We know that sk plus ky needs to be sy, so 21 plus 13 should give us 34, and it does. Let's talk about midpoints now. The midpoint of a section is exactly what you would expect it to be. The midpoint of a segment is the point that is in the middle of that segment. Okay? So, the midpoint of a segment is the segment that divides the segment into two equal parts. The word equal is key here. Two equal parts. Not just two parts, but two equal parts. A line, ray, or segment that intersects a segment at its midpoint is said to bisect the segment and is called the segment bisector. Again, we are not being that creative with the terminology here. Okay? In the figure that you see here, B is the midpoint of line AC, or I should say segment AC, since this is a line segment. And line L is a bisector of AC. So, below I give you a more formal definition of midpoint. The midpoint M of PQ, segment PQ, is the point between P and Q such that PM equals MQ. Okay, so in this figure here, the length of AB is equal to the length of BC. And that is indicated by these tick marks. Whenever you see tick marks, that means these two segments are the same length. So let's do an example for this one. If Q is the midpoint of segment PR, find the value of x. Well, if Q is the midpoint, then we know that PQ and QR are the same length. If they are the same length, then we can set them equal to each other. And again, I want to see the geometry. Show me the geometry step first. PQ is 7x minus 16. QR is 4x plus 2. Now we just solve for x. So let's subtract 4x from 7x, that gives us 3x. Let's add 16 to 2, that gives us 18. So x equals 6. In the next example, if H is the midpoint of segment GI, find GH. Okay? So first we have to find x. We do that by setting GH equal to HI. And we know we can do that because H is the midpoint, making these two segments the same length. So if GH is 5x plus 2, we will put that here. HI is 9x minus 10, so we put that here. Now let's solve for x. So let's subtract 5x from 9x, that gives us 4x. Let's add 10 to 2, so that gives us 12. So x equals 3. But we want to find GH. So we know that GH is 5x plus 2. So we are going to substitute in our value for x. So we have 15 plus 2. So GH is 17. All right, next we've got example 10. If R is the midpoint of Q segment QS, we're going to find QS. So we're going to find the length of the entire thing. Again, R is the midpoint, so this part and this part are the same length. So QR equals RS. So we can put in what each of those are. So let's subtract 2x from 5x. That gives us 3x. Let's add 17 to 16. Doing that gives us 33. And then divide each side by 3. We know that x is 11. Well, we don't have a statement for QS, but we know that QR plus RS is going to give us QS. Okay, so let's go ahead and find at least what QR is. QR equals 2x plus 16. Well, if x is 11, we have 22 plus 16, and that's going to give us 38. Okay, so we know that QS is equal to QR plus RS. That's the segment addition postulate. But we also know that RS is the same as QR. We had that written here. So let's substitute in QR for RS. Well, we found out that QR is 38. So 38 plus 38 is what QS will be. So QS is going to be 76. And for example 11, oops, let's not cut it off. If G is the midpoint of segment FH, and FH equals 6y minus 2, let's find y. Now you are reading that correctly. That is a y there. We're looking for y. But we're given x values for FG and GH. We're given those lengths in terms of x. We can still do this, okay? And here is how. We first of all know that FG has to equal GH, because G is the midpoint, which means this segment and this segment are the same length. So we can set them equal to each other. 4x plus 3 equals 7x minus 12. Now we are going to subtract 4x from each side, so 7x minus 4x gives us 3x. We'll add 12 to each side, so that gives us 15 on the other side. So x equals 5. Now, let's see what FG is. FG is 4x plus 3. Okay, so we're finding the length of this half of it. Well, 4 times 5 gives us 20, plus 3 gives us 23. Okay? Now, we know that FH, from the segment addition postulate, FH equals FG plus GH. And we know FG and GH are the same, so they're both 23. So let's go ahead and put those parts there. We also know that FH is 6y minus 2. So from here, we can simply solve for y. So 23 plus 23 gives us 46. So we'll do that step. If we add 2 to each side, we get 48, and then 48 divided by 6, y equals 8. So in doing these problems, you'll find this a lot in geometry. This is going to be a little bit like solving a puzzle, okay? Work with what you know and see where that takes you. We know that G is the midpoint, so we know FG equals GH. That right there can tell us what X is. That's something we didn't know starting out. We can use what we know to find what we don't know, but we still needed to find Y. So what else do we know? Well, we can find what FG is. We can find the length of that. We know that's the same as GH, so we can find out what numerical value FH is, and that's what we did on the right-hand side here. And then we can substitute in this statement for FH to find out what Y is. So you see that one thing kind of leads to the other. We're going to take an offshoot on this now and talk about congruent segments. So if AB equals CD, then the segments are congruent. If the length of AB and the length of CD are equal to one another, then they are congruent. That's the term that we use for this, okay? That's what we had with our two segments when we bisected with that midpoint. This is written as segment AB is congruent to CD. So you see example of that on these two number lines. The length of AB is 1, 2, 3, 4. The length of CD is 1, 2, 3, 4. They are in different places along the number line, but they are congruent. They are the same length. If you were to put them on top of each other, they would fit perfectly. So therefore they are congruent. So let's use that to try this example. If segment BD is congruent to segment BC, so BD is congruent to BC, which is notated here with the tick marks. BD equals 5x minus 26, so that's the length here. BC equals 2x plus 1, so that's the length here. And we know the length of AC, we want to find the length of AB. So let's start with what we know. We know that BD is congruent to BC, so therefore BD has to equal BC. And we have a statement for each of those. So if we plug in the statement for both of those, now we have something where we can solve for x, which we didn't know previously. So let's subtract 2x from each side. 5x minus 2x is 3x. Add 26 to 1, that gives us 27. So x equals 9. Now we know what x is. Let's use that to find BC. So BC equals 2x plus 1. If we substitute 9 in for x, we get 18 plus 1, which is 19. So the length of BC is 19. So finally, last step, let's use the segment addition postulate for this line segment. We know that AB plus BC equals AC. And we're looking for AB. So AB is what we're looking for. We just found that BC is 19. And we were told that AC is 43. So now all we have to do is subtract 19 from 43. And we find that AB equals 24. Okay, let's move on to an example that's got a little bit more to it. If segment LK is congruent to segment MK, so LK and MK both indicated by these tick marks, and we know the length of LK in these terms, so LK is here. We know that the length of KN, which is this short piece, is x plus 3. MN, the length of this whole piece, is 9x minus 11. And we know what KJ is. We are tasked with finding what LJ is. All right, again, let's start with what we know. What we know is the segment addition postulate. So the segment addition postulate, because we know what MK is. Now, I know we don't explicitly have what MK is listed up here, but we know that MK and LK are congruent. So LK, if LK is negative, is 7x minus 10, we can also say that MK is that as well. So we know what MK is, and we know what KN is, and we know what MN is. So we can use all of that to find out what X is. So we know that MK plus KN equals MN. MK is 7x minus 10. KN is x plus 3. And MN is 9x minus 11. Okay? So we can find what X is. 7x plus X is 8x. Negative 10 plus 3. So we got negative 10, we're adding 3 to it. That's going to give us negative 7. We still have 9x minus 11 on this side. So let's subtract 8x from 9x, that gives us x. Add 11 to negative 7, that gives us 4. So we know that x equals 4. So now that we have that piece of information, let's move on to finding what LJ is. Okay, so we know LK, we're given that. We know what KJ is. We need to find LJ. Again, segment addition postulate is what we're going to use. So LK plus KJ equals LJ. Well, LK we know is 7x minus 10 plus KJ, which is 28, equals LJ. But we know x is 4. So 7 times 4 minus 10 plus 28 equals LJ. 7 times 4 is 28. And let's see here. We have 28 minus 10. That gives us 18. And then 18 plus 28 gives us 46. Now, I went ahead and just put in what LK was here. If I wanted to do LK over to the side and then find that value and then plug that in and then just simply have 18 plus 28, that's perfectly fine. Remember, there's more than one way to get to the right place. As long as it's mathematically sound, we're good. All right, example 14. Segment EF bisects segment CD. Okay, so CG and GD are going to be congruent. So we know what CG is, we know what GD is, we know what EF is, which is this length for the whole thing here, and we know what GF is. We need to find what EG is. So let's start with what we know. We know we need to find X. And we can easily do that by using CG is equal to GD. Since these two segments are congruent, the length are equal to each other. So we have 5x minus 1 is equal to 7x minus 13. If we subtract 5x from each side, we get 2x on this side. If we add 13 to each side, we end up with 12 over here. And so x equals 6. So now that we know what x is, we can find what EF is, which is the length of the whole thing. EF is 6x minus 4. Plug in 6 for x, and you get 36 minus 4. So EF is going to be equal to 32. All right. Next, and finally, we use the segment addition postulate. We know EG plus GF equals EF. EG plus GF equals EF. Okay, so we know EG is what we're looking for. GF, we're told, is 13. EF, we just found, is 32. And so we subtract 13 from 32, and we get EG equals 19. So now you're familiar with how the midpoint works and segment addition postulate works. You can find all kinds of things based on the figure that you're given. Now let's move on to the midpoint formula. So if using the figures is not really your thing, the midpoint formula may be more your thing, because this is more of a plug and play sort of a situation. Okay, you can determine the midpoint of a segment on a number line or in the coordinate plane using one of the following formulas. So for a number line, it's just as simple as taking the two endpoint values, adding them together, and dividing by 2. Which makes sense. We're finding the average of those two numbers. The average is the number that's in the middle of those two numbers, so that would give you your midpoint. For a coordinate plane, this looks more complicated, but it really isn't. You're given a set of coordinates, x1, y1, and x2, y2. Those are your two endpoints. x1 plus x2 over 2 gives you your average x value. Your y1 plus y2 over 2 gives you your average y value. So you're basically doing what you did for the number line. You're just doing it for the x's and the y's separately, and your answer will be an ordered pair. So, example 15, we're going to find the midpoint of segment GH if you're given that coordinates for G and the coordinates for H. So, let's start with the x coordinate. For the x coordinate, we have 7 plus 9 over 2. Those are just our two x coordinates. 7 plus 9 is 16, and 16 divided by 2 is 8. For your y coordinate, we're going to do the same thing. -5 plus -1 over 2. That gives us -6 over 2. So our y coordinate is going to be -3. So our midpoint coordinates will be 8, -3. All right, let's do one more example of this. Okay. So I'm going to write it this way this time. We're going to do our x coordinates. So we've got -7 plus 3 over 2. And our y coordinates, 4 plus -4 over 2. Well, what that gives us is -7 plus 3 is -4 over 2. 4 plus -4 gives us 0 over 2. And so our x coordinate is -2. Our y coordinate is 0. Now, to find a missing endpoint, if we know what the midpoint is and we know one of the endpoints is, we can find what the other missing endpoint is. So we just went through this with our x coordinate. To find an unknown x coordinate, x1 plus x2 over 2 gives us the x coordinate of our midpoint. This can be rearranged into this. Okay, if we multiply each side by 2, we get 2xm, and then we subtract x1 from each side, you get 2xm minus x1. So this can be used to find your missing coordinate, x2, your missing endpoint, if you know what the midpoint is and what the other endpoint is. This can also be done with y. So let's do some examples of this. All right, so example 17. Let's find the coordinates of A if the midpoint, -1, 2, is the midpoint of segment AB, and B has the coordinates of 3, -5. Okay, so we're going to first find the coordinates of the x-coordinate of the missing endpoint. So we're going to use this, and then we're going to come over and do the same for our y-coordinate. So let's start with the x-coordinate. So we have 2. Our x from our midpoint is -1. And the x from our other endpoint is 3. So that gives us -2 minus 3, which is -5. For y, we have 2 times our missing, our midpoint, which is 2, minus the endpoint that we have, which is -5 from the y-coordinate. 4 minus -5 is 4 plus 5, which gives us 9. So the coordinates of A are -5, 9. All right, for example 18, same sort of deal. And I'm not going to write the formula again. We've got it up here at the top. So we've got 2 times -5, because K is our midpoint. The other endpoint, x value, is -8, so we got minus -8. So that's -10 plus 8, which gives us -2. For our missing y, we have 2 times 10 minus 6. So that's 20 minus 6, which gives us 14. So our coordinates are 2, 14, and that is for J. And then for example 19, again, we're finding the coordinates of R if Q is the midpoint with these coordinates, and P, our other endpoint, has these coordinates. So we've got x2 equals 2 times our midpoint x, which is -1, minus our endpoint x, which is 5. So -2 minus 5 gives us -7. Here we have 2 times our y midpoint minus our y endpoint, which is 6. So we got 6 minus 6, which is 0. So the coordinates of R are -7, 0. All right, last thing we want to go over in this section, distance formula. So we can find the distance between two endpoints, or the length of a segment, using the distance formula, okay? And that is presented here. And you'll get into more as to where this comes from. A lot of this comes from right triangles and things of that nature. We'll be discussing that more toward Unit 4, 5, and 6 when we do triangles. For now, this is the distance formula. It is the square root of the difference of our x-coordinates squared plus the difference of our y-coordinates squared. Okay? So this right now is a formula that you mainly just need to know. Okay? So let's use this formula. So in example 20, we are asked to find the distance between the 2 points on the graph. Well, we can find what those ordered pairs are. Okay? We're going to do our x1, y1 coordinates and our x2, y2 coordinates. Okay? So let's make this our first one, and this one our second one. So the coordinates for our first point are -5, 3. The coordinates for our second point are -2, -3. Now we are going to plug this into the distance formula. This is certainly something that you're going to want to use your calculator for as well. So we've got -5. Well, let's just write what the formula is first. That way we're on the same page. x2 minus x1 squared plus y2 minus y1 squared. So now that we've got it all lined out, all we got to do is substitute in. That's minus. So x2 is going to be -5. In fact, x2 is -2, so there you go, -2 there. Let's make x1 -5. Okay, so I'm just looking for these things and plugging them in. Plus y2, which is -3, minus y1, which is 3. And that's going to be squared. Okay, so now, if you put this into your calculator, you can simplify this down if you'd like to some degree before you put in your calculator, but if you put it in your calculator, you're going to get approximately 6.7, and that is your distance. Okay, all this is math at this point. Use your order of operations. Do what's in the parentheses, do your exponents, add those things together, do your square root. 21 is a little bit easier because we are going a little bit more straightforward with coordinates just being given to you. You don't have to find the coordinates. So we have d equals the square root. We're going to do the difference of our x's. So we have -4 minus 3. And it doesn't matter which one you do, in which order, just as long as you follow your x2's go together with your y2 and your x1 goes with your x1. So we did -4 first. Let's do 1 next, minus -1. And if you put this into your calculator, you're going to get approximately 7.3. For example 22, we are, again, going to plug in all of our things here. So we've got the difference of our x's squared plus the difference of our y's squared. You put that into your calculator and you're going to get approximately 18.7. So those are just some straight examples for finding distance of lines with the two endpoints. But let's use this a little bit. So example 23, if we are given these coordinates for these 4 points, we're asked to determine if segment AB is congruent to segment CD. So if they are congruent, then the distance formula should give us the same value for both. So let's see if that is the case. So I am going to do my difference of, first for AB, I'm going to do my difference of x's, so 0 minus 8 squared, plus 4 minus 4 squared. This one we can actually do by hand. It's a little bit easier. So we have the square root of -8 squared, because 0 minus 8. So we do our parentheses. We get -8 squared. 4 minus 4, we get 0 squared. So we have the square root of 64 plus 0, which is just the square root of 64, which is 8. So that one comes out nice and even. So if CD is also 8, then we can say they are congruent. But the only way to find out is to do our distance formula. So we have 6 minus 6 squared, the difference of our x's, plus the difference of our y's, 6 minus negative 2 squared. Okay, so now we have the square root of 0 squared plus 6 minus negative 2, that's going to be 8 squared. So we have the square root of 0 plus 64, which is just the square root of 64, which is also 8. So we can say yes, AB, segment AB is congruent to segment CD. Last example for this section. We are asked to find the perimeter of a triangle, DEV, given that D is located at this coordinate, E is located at this coordinate, and V is located at this coordinate. Remember, perimeter is the measure of the outer edges, okay, the length of the edges of the triangle. So to do this, we are going to do this for each line segment. So for DE, we have the distance being the square root of, well, let's see, we've got D, so our x's, 1 minus 2 squared plus 1 minus 3 squared. Put that into your calculator and you're going to find that the distance is approximately 2.2. If we go to EV, the next line segment, the distance is going to be 2 minus 3 squared plus 3 minus 0 squared. Difference of our x's, difference of our y's. Put that in your calculator, you get approximately 3.2. And then finally, DV. The distance of DV, we can just do 1 minus 3 squared plus 1 minus 0 squared. Again, use your calculator, you find it's approximately 2.2. And now to find the perimeter, we just add DE plus EV plus DV. So we've got 2.2 plus 3.2 plus 2.2, and that's going to give you 7.6. And so that would be the perimeter of that triangle. Okay, so that concludes this section. It was a bit of a long section on segment relationships. The third section that's coming up will be on angle relationships. So we'll start talking about angles here in the next section.